As we approach this lesson, I want to remind you of how to solve logarithmic equations from your pre-calc course. So I have two very simple ones on the screen. The log of x is equal to 4. So you need to think about, well, what is the base when no log or when no base is written? Hopefully you know the base is 10. So what you need to do is what we call exponentiating each side. So we're going to make the base on each side be 10. By doing that, 10 to the log of x, well, these things undo each other, and it leaves you with x equals 10 to the fourth, or x is equal to 10,000. To solve the ln of y is equal to 12, think about what is the base on the natural log. It's e. So you're going to exponentiate, this time using e as the base, which is going to produce y is equal to e to the 12th, and you can use your calculator to evaluate that. That's a large number. If we were to approximate, it would be 162,754.8. So as explained in the AP Classroom video, one of the goals of re-expressing data is to make your data more linear so that we can use a least square regression line. Sometimes other models are better, could be an exponential model, a cubic model. However, those models are outside the scope of an AP statistics course. So the goal of statistics is to use a linear model. So if we can re-express the data and make our data more linear, then we can use the least square regression line to make predictions. Most commonly on the AP exam, you will already be given an equation that's been re-expressed, and you just have to interpret it. So let's look at a few examples like that. This one says a regression of the square root of y versus x was performed, and the following least square regression line is the square root of the predicted y is equal to 5.28 minus 0.197x. Okay, so you can see that they took the square root of their predictions. So what is the prediction when x is 10? So we're really just doing some algebra here. I'm going to copy carefully my equation, and I'm going to plug in 10 for my explanatory variable. When I type the right side into my calculator, I get 3.248. And now I need to get the predicted y. A common error, especially in multiple choice questions, is that 3.248 would be one of the answers. But we are going to square both sides to get rid of the square root, which is going to leave me with y hat, or the predicted y, is equal to 10.55. And I should probably say approximately equal to, since I rounded. In the second one, the length of a year for a planet based on its distance from the sun is modeled by the ln of x and the ln of y. So my explanatory variable and my response variable, they've taken the ln of both of these, the natural log, probably to straighten my data. And here is my regression model. And I'm asked, if a planet existed between Mars and Jupiter at 313 million miles, what is the predicted length of a year? So 313 million miles is going to be what I'm substituting in right here. But I notice that my explanatory variable is in millions of miles, so I'm really just plugging in 313. So what I'm going to do to solve this is just substitute this entire right side into my calculator. Don't miss the ln of 313. That's 1.5008 times that. I get 1.8193 approximately, and I still have the ln of the predicted years over here. So I need to get rid of the ln. So I need to exponentiate. The base of the natural log is e, So when I do that, that produces just y hat, or the predicted years, is equal to, and type in e to the 1.8193, and that gives me approximately 6.168, and that is Earth years for my variable on my response variable. I should say my units on my response variable. In our third example, bacteria are allowed to grow in a petri dish. The number of bacteria is recorded each hour. This data results in an exponential graph. However, if we take the logarithm of the y values, we can get the following linear model. Okay, so they've explained why they did it. They were able to straighten their data with this model, and we're going to predict the number of bacteria after 6 hours. So pause the video and see if you can do this one. So in this one, I substitute in 6. I get the log of the predicted y is equal to 2.891. To get rid of the log, I exponentiate. It has a base of 10. So this produces y hat equals, or I should again say y hat is approximately equal to 778.04, and this is bacteria. Here's a sample multiple choice question. It says 7, but this is our fourth one. It is easy to measure the circumference of a tree's trunk, but not so easy to measure its height. Foresters developed a model for ponderosa pines that they used to predict trees' height in feet from the circumference of its trunk, in inches. Okay, so you can see that they took the ln, the natural log of both the response and your explanatory variable here. Must again been to straighten their data. A lumberjack finds a tree with a circumference of 60 inches. How tall does this model estimate the tree to be? Again, pause and see if you can come up with the answer. Begin by substituting, then put the right side on your calculator because the calculator can handle the natural log of 60. I get the ln of the predicted h is equal to 4.53. To solve for just h hat, I need to exponentiate. The base is e. So this produces a predicted height of, again, approximately 92.95 feet. So when I look at the multiple choice, I'm going with this one here. Just to point out, some people are going to go with 5 feet because they're going to get that 4.53 and stop right there. So, just watch for that. Hopefully you would recognize that it's really not logical to have a tree with a circumference of 60 inches. That's 5 feet tall, but you never know.